Okay, so let's just unpack this right away. Today we are talking about walls.
Which I know sounds,
Yeah, I know what you're thinking out there.
yeah,
You tuned in for a deep dive, not a lesson on drywall or interior decorating.
right.
But stick with me here, because the walls we're looking at today are, they're arguably the unsung heroes of the entire global economy.
They really are. I mean, without them, your car, your coffee, probably the device you're listening to this on right now, it wouldn't have made it across the ocean.
Exactly. So we are diving into the technical documentation surrounding bulkheads. Specifically, we're looking at a document simply called Four Bulkheads.
Which sounds very dry.
It sounds incredibly dry, I admit. But honestly, before reading through this stack of papers, I just thought of a bulkhead as just a divider, like a partition in a conference room or the wall in front of the emergency exit row on a plane.
A lot of people do, but the engineering reality is so much more intense.
It is. And our mission for this deep dive is really to shift that perspective for you. You need to look at the actual anatomy of a ship.
Because if you imagine a vessel not just as a vehicle, but as a floating city, a city that has to survive earthquakes, which out there are waves and floods and fires all simultaneously,
Right.
the bulkhead is the thing holding that entire city together.
I really love that image of the floating city. So for everyone listening,
Mm-hmm.
let's just set the scene. I want you to imagine you are standing inside the massive hollow belly of a cargo ship.
Maybe a bulk carrier.
Yeah, a bulk carrier. It's cavernous, it echoes, it's just steel everywhere. And looking around, you see these massive vertical partitions rising from the floor.
The double bottom.
Right, the double bottom goes all the way up to the main deck. Those are the bulkheads.
Right. And strictly speaking, the definition is simple enough. Bulkheads are the inner walls within the hull of a ship used to separate it into smaller compartments.
But if we just stop at the definition, we kind of miss the whole point.
We do, because the why behind them, that is where the physics comes in. This is about compartmentalization.
Compartmentalization,
No.
which, it's a term we usually use in psychology for coping with stress.
Yeah.
But here it's about the ship coping with physics. The source material actually outlines four main purposes for these things. And I want to start with the one that surprised me the most, which is structural integrity.
Why did that surprise you?
Well, I just always assumed the outer shell, the hull, did all the heavy lifting, like an eggshell.
Ah, right.
The inside is just empty space, right? But the docs say these internal walls are totally critical for the ship's overall strength.
It's a really common misconception, actually. The hull is the skin, sure, but the bulkheads are the ribs. They're the backbone. Think about a cardboard box.
Okay.
If you have a big, empty cardboard box and you push down on the top of it, it crushes pretty easily. It'd buckle.
Right. It has no internal resistance.
Exactly. Now imagine you put a cardboard divider inside that box, right in the middle, glued to the sides. Suddenly you can stack a lot more weight on top of it.
Oh, wow. Yeah.
And that is exactly what the source material is explaining. Dividing the ship into smaller parts contributes to stiffening the hull.
Because these bulkheads actually support the deck above them.
They do. They transmit the weight of the cargo, the cranes, the deck itself, straight down to the strong structure at the bottom of the ship.
So they are load-bearing walls, just on a massive industrial scale.
Massive. They prevent the hull from basically collapsing in on itself under the weight of the ocean or its own cargo.
Okay, so that's purpose number one, keep the ship from getting crushed.
Yeah.
Number two is the one we probably all know from the movies, right?
Yeah.
Flood containment, the unsinkable factor.
Right. The document explicitly mentions that bulkheads add the possibility to seal damaged compartments and isolate them from the rest of the ship. It's the isolation concept.
But let's play devil's advocate for a second. If I poke a hole in a bucket, the bucket sinks. Why does putting a wall inside the bucket save it?
Because you aren't poking a hole in a bucket anymore. You're poking a hole in a honeycomb.
Okay.
If a ship hits a rock or an iceberg and water breaches the hull, that water wants to rush from the bow all the way to the stern. It's
Right.
incredibly heavy, and it absolutely kills your buoyancy. But if you have watertight bulkheads, the water is trapped in just one room. The rest of the ship stays perfectly dry, maintains its buoyancy, and you stay afloat.
So it's basically damage control built directly into the architecture of the ship.
Precisely. It's passive survival.
Okay, so we have structural strength and flood control. Those are the survival features. But most ships, thankfully, don't spend their time sinking.
No, they do not.
They spend their time working. And that brings us to the third purpose from the text, which is storage and logistics.
And this is really the economic driver. You cannot just have a giant hollow bucket if you are shipping complex goods.
Because things would get messy.
Very messy. You might have grain in one hold, machinery in another, or liquid bulk in a third. You absolutely cannot let those mix.
Yeah, I'd imagine mixing grain with crude oil would result in a very unhappy customer.
Extremely unhappy and honestly dangerous loose cargo shifts. If you have a massive open space and the ship rolls in a wave, the cargo slides all the way to one side. That momentum can capsize a vessel, so bulkheads act as baffles, keeping the loads centered and separated.
And the layout changes depending on the vessel type, too, but the principle is always the same. Subdivision for utility.
Exactly.
And finally, the fourth pillar mentioned in the text, fire safety.
Mm.
This one actually gave me pause.
Why is that?
Well, we always think about water being the enemy of a ship, But fire on the open ocean is terrifying. There's literally nowhere to run.
It is the absolute worst-case scenario for a mariner, bar none. And the source notes that certain types of bulkheads are specifically designed to be fire-resistant.
So it acts as a firewall, literally.
Literally a firewall. If a fire starts in the engine room, you seal the bulkheads. You starve it of oxygen, or at least you prevent the intense heat and flames from spreading to the cargo holds or the crew quarters.
It buys the crew time.
It buys them time to fight the fire, or, if it comes to it, abandon ship safely.
So we've established that these things are keeping the ship from crushing, sinking, mixing cargo, and burning down. Which is not bad for a wall.
Not bad at all.
But here's where it gets really interesting, where I want to push on the details a bit from the source material. The orientation. Because apparently not all bulkheads run the same way,
Yeah.
and they don't do the same jobs.
No, they don't. And this is a critical distinction in naval architecture. We have transverse bulkheads and longitudinal bulkheads.
Okay, let's do transverse first. These run side to side, right? Port to starboard.
Correct.
The text says they stiffen the structure of the hull, preventing deformation and racking stresses. Now, racking stresses sounds painful. What exactly is happening to the ship there?
Okay, imagine the ship is in really rough seas. A massive wave hits the front left corner, the port bow, but the back right, the starboard stern, is down in a trough between waves.
Okay.
The ocean is literally trying to twist the ship the way you would twist a wet towel to wring it out.
That is a staggering amount of torque on a steel structure.
Immense torque. Racking is that cross-sectional distortion. Transverse bulkheads act like rigid ribs inside the chest cavity. They lock the shape in place so the ship doesn't twist itself apart.
Got it. So transverse handles the twisting. Then we have the longitudinal bulkheads.
Yes.
These run fore and aft, front to back. And the text says these are particularly essential for larger vessels like tankers. Why specifically tankers?
Think about the sheer length of those things. A supertanker can be a quarter-mile long. When a ship that size rides over ocean swells, you get two specific structural phenomena: hogging and sagging.
Hogging and sagging, which sound like agricultural terms to me.
I know, but it's purely structural. Imagine a giant wave is right in the middle of the ship.
Okay.
The middle is pushed up by the water, but the ends, the bow and stern, are sort of hanging in the air over the troughs. Gravity pulls the ends down, and the ship wants to snap in half over the wave like a twig over your knee. That's hogging.
Yikes. Okay, and sagging.
Sagging is the exact opposite. The waves are supporting the ends of the ship, but the middle is totally unsupported over a trough. The heavy middle wants to buckle downwards.
I see.
So longitudinal bulkheads act like a secondary internal backbone running the entire length of the vessel to prevent that snapping or buckling.
So just to summarize that, transverse stops the twisting, and longitudinal stops the snapping.
That's a simplified way to look at it, but yeah, it's accurate.
Now, this brings us to the part of the documentation that I really want to dig into. It feels almost like an engineering showdown in the text.
The construction styles.
Exactly. We have two ways to build these things, the plain bulkhead and the corrugated bulkhead. And looking at the diagrams in the source, figures 16 and 17, the difference is just night and day.
It is a classic case of old-school brute force versus elegant geometry.
Let's start with the plain bulkhead. The text says these are constructed from flat plates, which sounds simple enough, but looking at figure 16, it doesn't look simple at all. It looks like a cluttered mess.
Well, here's the fundamental problem. A flat sheet of steel is great at holding water back, but it is terrible at standing up straight under pressure. It's floppy.
Really, even thick steel.
Even thick steel. If you put thousands of tons of grain or water against a flat steel sheet, it will just bulge and eventually collapse.
So how do they fix it?
Stiffeners.
Are the-
The source notes, they have to be reinforced by stiffeners. If you look at the diagram, these are those vertical beams you see spaced out every 2 feet or so.
Right.
They look like heavy T-beams or angle irons welded vertically straight from the floor up to the ceiling.
It looks like a cage, honestly. Or the back of a theater stage set.
It is a cage.
Yeah.
And think about the construction process for a second. You have to lay out this massive flat plate. Then you have to manufacture dozens of these heavy steel beams. Then a crew has to weld each one onto the plate.
That sounds incredibly tedious.
It's hundreds of meters of continuous welding. It's heat, it's intense labor, it's time, and most importantly, it's weight.
Right. And I assume in commercial shipping, weight is the ultimate enemy.
Weight is money. Every ton of steel you use to build the internal wall is a ton of paying cargo you can't carry. Plus, all those nooks and crannies between the stiffenals are a complete nightmare to clean and paint.
Which perfectly sets up the challenger.
Yes.
The corrugated bulkhead.
Yes.
The source presents this as the superior solution. But I have to be honest, when I read the word corrugated, I instantly think of a cheap cardboard box. It sounds flimsy.
It sounds flimsy, but the physics dictate that it is actually stronger.
Explain that to me. Because the text says they are constructed from corrugated metal plates and, quote, naturally provide more rigidity. How does bending the metal make it stronger? You aren't adding any material.
You aren't adding material, you're adding depth. Think about a flat piece of paper.
Okay.
If you hold it out by one edge, it just flocks down. But if you fold that exact same piece of paper into a zigzag like a paper fan and hold it out, it stays perfectly rigid.
The fold gives it structure.
Exactly. In engineering terms, you are increasing the moment of inertia. By moving the metal away from the neutral axis, the center line, you make it much harder to bend. The shape itself takes the load.
And the kicker here, according to the text, is, quote, as a result, these bulkheads do not need to be reinforced with stiffeners.
That is the big aha moment right there. You can delete all those vertical beams. You don't need the T-bars. You don't need the angle irons. You just have the wavy wall.
That seems like a massive advantage. You remove material and the structure gets stronger.
It gets stronger and lighter. The source explicitly states these bulkheads are lighter and stronger than the plain bulkheads.
Wow.
It is a huge win for efficiency. You save steel, you save thousands of man-hours of welding, and you get a ship that is lighter overall, meaning it burns less fuel or carries more cargo.
It's so elegant. I'm looking at the diagram for the corrugated bulkhead now, figure 17. It's so clean compared to the plain one. Just these vertical zigzag lines. It almost looks futuristic.
It is cleaner, but I do want to be careful not to oversell the simplicity here. If we really look at the anatomy in the diagram, it's not just a wavy sheet of metal floating in space. The connection points are highly complex.
Right. I see a few labels here that sound pretty unique. Shutter plates, diaphragms.
Let's walk through those.
Yeah, let's walk through this diagram because this is where the rubber meets the road.
Okay, so let's look at the bottom of the corrugated wall, right where it meets the floor, which is the tank top or double bottom. You see those angled plates labeled shutter plates.
Yeah, they look like little ramps at the bottom of the zigzags.
They are ramps. Think about the logistics again. If you are carrying coal or grain or fertilizer, if you had a flat connection at the bottom, the material would get stuck in the deep corners of the corrugation.
Oh, like dust in the corner of a room that the broom can't reach.
Exactly. But on a cargo ship, that dust is tons of rotting green. If grain gets stuck down there and gets wet, it rots, it smells, it can release toxic gases. Or worse, some cargoes, like coal, can spontaneously combust if they're left in a pile.
That goes back to the fire safety issue.
Right. So the shutter plate is angled, usually at 45 degrees, to shed the cargo down to the flat floor so the unloading grabs can easily scoop it all up.
So it's essentially a self-cleaning feature built into the wall.
It's essential hygiene for the ship.
Okay, what about diaphragms? The diagram points to something inside the corrugation folds.
Right. Even though the wavy shape is very strong against bending, it can still be crushed if the forces are coming from weird angles. A diaphragm is a horizontal plate welded horizontally inside the hollow part of the corrugation.
Oh, I see it.
It acts like a bridge, keeping the shape true so the fold doesn't flatten out under extreme stress.
So it's hidden strength.
Exactly. And look at the stool.
The stool.
The bottom section where the bulkhead mounts to the floor is often called the lower stool. It's a box-like structure that transitions the forces from the wavy wall into the flat floor. You can't just weld a zigzag line directly to a flat plate. The stress concentration would just crack the weld. You need a transition piece to spread the load. That's the stool.
I see. So even with the simple corrugated design, you still need these specialized components.
Yeah.
The shutter plates, diaphragms, stools. You need them to make it actually work in the real world.
Absolutely. Engineering is rarely about finding a magic bullet that solves everything with zero downsides. It's almost always about trade-offs. But in this case, the trade-off is overwhelmingly in favor of corrugation.
The contrast is still huge, though. Just visually comparing the plain bulkhead image, which really does look like a heavy construction site, to the corrugated one. It makes you wonder why we ever built them the old way to begin with.
Well, plain bulkheads are still used in some specific places.
Oh, really?
Yeah, sometimes you need a perfectly flat wall for mounting heavy equipment, or you're in tight spaces where the deep corrugation takes up too much room volume-wise. But for the main cargo holds, corrugation is king.
It reflects a broader trend in engineering, doesn't it? Moving away from brute force, just throwing more metal at a problem, to smart geometry.
It does. It's about really understanding the material. Steel is heavy. Air is light. If you can shape the steel to trap air, like in the corrugation folds, and use that physical shape for strength, you win.
So bringing this back to you, our listener, who might be sitting in traffic right now or doing the dishes, why should you care about the difference between a stiffener and a corrugation?
I think it matters because it changes how you see the built world around you.
Yeah.
Next time you see a shipping container on a truck, look at the sides. They are corrugated. Why? Because they need to be stackable and light. Next time you step on a passenger ferry, look at the walls. Realize that they aren't just room partitions, they are active structural elements fighting gravity and water pressure every single second.
And they are doing it efficiently. That's the part that really sticks with me from these documents, the idea that you can make something better by taking things away, removing the heavy stiffeners, and just changing the shape.
It is the ultimate work smarter, not harder.
We've covered a lot of ground here today. We defined the bulkhead as way more than just a wall. We unpacked the 4 pillars: structural integrity, flood containment, storage, and fire safety.
And we looked at the orientation, how transverse stops the twist and longitudinal stops the snap.
And we crowned a winner in the construction showdown.
The corrugated bulkhead. Long may it rain.
Long may it rain. But before we wrap up this deep dive, I want to leave everyone with a final thought. We talked about how the plain bulkhead tries to solve the problem of weakness by adding more stuff, more stiffeners, more welds, more weight. It complicates the system just to make it work.
And the corrugated bulkhead solves it by questioning the fundamental shape of the wall itself.
Which raises a really provocative question for us, not just in maritime engineering, but in how we solve problems in our own lives or jobs.
Oh, absolutely.
How often do we try to fix a weak system by just adding more stiffeners?
Yeah.
More rules, more meetings, more layers of management.
When what we really need to do is stop, look at the basic design, and just corrugate it. Change the shape of the solution rather than constantly reinforcing a bad one.
That is a powerful thought to chew on. Sometimes you don't need more support, you just need a better shape. Thanks for joining us on this deep dive into the hidden backbone of the high seas.
It was a pleasure to be here.
And to you listening, keep exploring the hidden details. You never know what keeps you afloat until you look inside. We'll catch you on the next deep dive.